Hi, I'm Alex. This is Oh, That's Why, a podcast about JavaScript, finally making sense. Let's dig in. Here is a bug that has confused almost every JavaScript developer at some point. You have an object. You assign it to a new variable. You change a property on the new variable. And then you check the original object, and its property changed too. You didn't touch the original. You changed the copy, and yet the original changed. Then you try the same thing with a number. Assign a number to a new variable. Change the new variable. Check the original. It didn't change. Same operation, completely different result. And nothing in the syntax tells you why. I spent an embarrassingly long time just accepting this. Objects are weird. They behave differently from numbers. Fine. Moving on. But there is a reason. A specific physical reason rooted in how your computer stores data in memory. And once you understand it, this confusion not only disappears, it becomes completely predictable. Where do your variables actually live? Think about a workspace, two different places where you might store information. The first is a whiteboard, right in front of you, always visible, immediately accessible. You write something, you can read it in a fraction of a second. When you erase it, it's gone. Fast, limited in space, designed for things you need right now. For quick, immediate information, a number, a name, a true or false answer, it is perfect. The second is a filing cabinet across the room. Much larger, can hold far more. Getting something from it takes more steps. Slower to access, but it can hold things of arbitrary size and complexity, and documents stored there persist beyond the current task. In JavaScript's memory model, the whiteboard is called the stack. The filing cabinet is called the heap. The stack is fast, limited, and orderly. It grows and shrinks in a strict pattern. Remember our plates from episode 3. Each execution context that goes onto the call stack gets a portion of stack memory. When the context is popped off, that memory is released automatically. Clean, predictable. The heap is large, flexible, and less orderly. It is where complex data lives, things whose size isn't known in advance, things that need to outlive the execution context that created them. Allocating and releasing heap memory is more complicated, which is why JavaScript has a garbage collector. We will talk about that next week. What lives on the whiteboard and what lives in the filing cabinet? That depends on whether your data is a primitive or an object. Primitives, numbers, strings, booleans, null, undefined, symbol, and big int, are stored directly on the stack. When you declare a variable and assign it a primitive, the actual value goes right onto the stack, attached to the variable name. Small, fixed size, immediate. When you assign a primitive variable to another variable, JavaScript copies the value. Not a reference, a complete, independent copy. Two variables, two distinct pieces of data. Changing one has absolutely no effect on the other. Objects are different. When you create an object, the actual data goes on the heap. But on the stack, where your variable lives, JavaScript doesn't store the object itself. It stores a reference, an address, a pointer to where the object lives on the heap. This is the key. The variable on the stack holds the address, not the data. When you assign an object variable to another variable, JavaScript copies the reference, not the object, the address. Both variables now point to the same object on the heap. When you modify the object through either variable, you are modifying the one object they both point to. That is why the original changes when you modify the copy, because there is no copy. There is one object and two variables pointing at it. Now, const. This is where people get confused. You declare an object with const. You try to reassign the variable to a different object, and that fails. Const is working correctly. The reference on the stack cannot be changed. But then you modify a property of the object, and that works. How? Because const protects the reference, not the object. The address on the stack is locked. You cannot point the variable at a different object, but the object on the heap is entirely separate. Const has no opinion about it. Add properties, remove properties, change values, the address stays the same. Const is satisfied. This is why const does not mean immutable when it comes to objects. It means the reference is fixed. The data it points to is not. The accidental mutation trap is the one I see most often. You pass an object to a function. The function modifies a property. You check the original after the function returns, and it has changed. You expected the function to work on its own copy. It did not. Because you passed a reference. The function received a pointer to the same object on the heap. Any modifications inside the function are modifications to the shared object. This is not a bug in JavaScript. It is expected behavior once you understand the memory model. The fix, when you genuinely need an independent copy, is to create one explicitly. Spread syntax for shallow objects. A structured deep copy for nested ones. Object equality is the second trap, and this one hits hardest in tests. Two objects that look identical, same properties, same values, are not equal if they live at different addresses on the heap. The comparison checks whether the references point to the same object, not whether the contents match. Two separately created objects are two different things, no matter how similar they appear. Tests fail. Developers are confused. Stack Overflow is consulted. The third trap connects directly back to last week. When a closure holds a reference to an object, it holds the address to the heap. The closure keeps that heap memory alive. A closed-over number takes a tiny amount of stack space. A closed-over object might reference an entire tree of heap-allocated data. In long-running applications, closures that hold onto large objects, especially in event listeners that are never removed, accumulate quietly. Being deliberate about what your closures capture matters more when those values are objects. Primitives live on the stack, copied by value. Objects live on the heap, passed by reference. Once you know which is which, a whole category of bugs becomes obvious. The whiteboard for the quick stuff, the filing cabinet for the complex stuff. And the variable you see in your code is always, for objects, just a note on the whiteboard that says where the real thing is stored. This also explains why closures work the way they do. The closed-over variables that persist after a function's context is gone? If they are objects, what persists is the reference on the stack, and the object stays alive on the heap because something is pointing at it. The garbage collector sees the reference and leaves the data alone. More on that next week. The companion article on Medium has a visual walkthrough, exactly what the stack and heap look like during a function call. Link is in the show notes. Next week, garbage collection. JavaScript eventually cleans up the heap. But what if it misses something? What causes memory leaks, and how do you find them? I'm Alex Vega. This is Oh, That's Why. The next time an object changes in a way you didn't expect, you'll know exactly where to look. See you next week.